Hi guys, today we're going to finish off all our calculations for thermochemistry. We're going to do 4 parts. We hope we can finish all in time. The first one, of course, is this one called calculations of summation of heat of formation and heat of reaction. Okay. The second one is using double bond energy. Here we are. Okay, bond energy and heat of atomization and heat of reaction. Okay. This is basically to do with the covalent bonds and almost in gaseous system of this. Okay. The third one, of course, we're going to talk about is your heat of hydration. Here we are. Okay, I'll give you the definition for all of this: heat of hydration and heat of solution. Okay. This is more specific for your AS. Because for A2, there's another heat of hydration. Okay. Last one, of course, is heat of neutralization. So all this, when we're done, you will finish off all the calculations to do with thermochemistry. Okay, now let's get started. Okay, so the first, of course, is this thing, the using of this special formula. Well, don't care we derive it. Okay, this one here, right? This is a very useful formula, and it's only for heat of formation when heat of formation is provided. So I got the definition here. Heat of formation is of a compound. The heat change in 1 mole of the compound is formed from its elements under standard condition. Okay, right? First, heat of reaction is general. This is general term. Okay, so they normally use this idea of heat of reaction means they don't care what sort of reaction it is. Right? Remember, just to go over again. Yeah? The heat change when the moles or the number of moles of reactants. The first one is react to give the products or the number of moles of products. Number of moles of products as shown in equation. Okay, remember here the keyword is equation under standard conditions, right? So this is the heat of reaction. This is general for any type of reaction. So now this is quite simple. Heat of reaction here, R is any reaction we do, right? But here this part here you must be provided with all the heat of formation. So summation of heat of products, formation for products minus the summation of heat of formation for reactants. It's quite simple. Right? It's basically maths. Now let me start with the first one here. DME may be synthesized from methanol. Now this is your methanol, right? CH3OH. Okay. Relevant enthalpy changes of formation. See now, is delta H here and F. For the questions given below, see all are right delta HF. So once you see the delta HF, that means again, I can apply this formula, right? So use this value to calculate for heat of reaction, say general, okay, for synthesis of your DME, following the equation here. Include sign, very important, sign and of course units. So remember, since you're given here a formation here, and this is a general reaction, so the delta H of reaction here, RECTF, okay, right? Since it's standard here, or standard. So see now, summation of products minus summation of heat of reaction for heat of formation for your reactants. Okay, very simple, but here the notice is this per mole. Okay, so here this is first. Okay, this is your CH3COCH3. Okay, it's like a ether thing. Okay, so remember this is the first one here. So it's 1 mole, so it's 1 times minus 8184 bracket, and of course here is a water. So 1 mole. So 1 times minus, now put the bracket and the minus sign here, because when you remove the brackets, the sign changes. Okay, maths lah. Minus again, bracket here, 2. Why 2? Because 2 moles here. 2 times this one here, minus 2. Okay, minus. Okay, so make sure you put the brackets. You don't put the brackets, get it wrong because of the signs. Okay, so you put on minus is minus 470. So minus and minus get positive. So the answer is plus 8. The sign is very important. One is for the plus, okay, and the kilojoules per mole. Okay, now you see, isn't it? It's all maths, but the thing is to use a formula. Okay, now another one here. We just go to a couple of them just to show the different type of application. Okay, the standard enthalpy change for formation of ammonia and water. Now this one, this is okay. Given below. So formation again. What is it for formation here? That means good, I can use the formula. Okay. Use this data to calculate and the value for heat of reaction, right? And this is the reaction here. Ammonia plus oxygen give you, okay? You don't calculate reaction as long as it's a reaction and between this is the general thing. Of course, you can say it's combustion, but it's not complete. This and O only not NO2. Okay, so don't care. Just this is a reaction. Okay, so it's on here. So again, because again the heat of formation, and you're asked to calculate the standard heat of formation of this fellow here. Okay, so you know this one here, given here, the heat of formation. Oxygen is 0. Why? Because for all elements, remember now, see here, this is the one of the conditions you must remember. All elements, let me just put here, highlight, okay, red color, okay, see here. All elements, right, under standard conditions have 0 enthalpy, very important. All elements are oxygen, hydrogen, nitrogen, whatever, as long as the elements is 0. So you apply this here is 0. Right, so this is okay. Here, this is 0. So summation of products, 4 moles. Okay, 4 times NO. Right, NO you don't know, so we can put X. Right, X here for X. 6 times your water. See, 1 mole of water is -242. So 6 times this way. Make sure the bracket here and minus sign here. Right, put everything down first because you can make mistake. I make a lot of mistakes like this. Minus, remember the formula? Summation of 4 times this. Why 4? 4 here, 4 moles of ammonia times minus, okay, minus sign is here, make sure. Point here, make sure. And 5 times 0. Why? Because oxygen is element, so it's 0 enthalpy. So here, be careful, the signs are all very important. Once you pick the signs wrong, everything's wrong. Okay? So you can do your maths here and you remove the bracket, become positive, isn't it? So you bring over this side, right? Bring over this side here, you get this one here, and this is our answer plus. Okay, the sign will come automatically when you follow the rules. Okay, easy, is it? All right. Now another one is here. Now here is just to the same thing lah here. Right. So again, the heat of formation of carbon dioxide. Again, the formation of water, formation of formitting. What's the temperature for combustion? Of course, here you need to write the equation lah. If you don't write the equation, that means you die lah. Okay. Combustion means 1 mole of the compound is fully combusted. Isn't it? So 1 carbon here, 1 carbon here, you get 2 oxygen, 2 here, 4, so maybe 2 here, right? So it's balanced here. Again, you put your formula. Heat of reaction, of course, this reaction is called combustion, right? So it's a name for this. So summation of the products. Okay, carbon dioxide is -394, you see here, right? 2 moles of water, 2 times 286, minus here, okay? Minus, of course, the reagents, which is your CH4 here, methane, minus 74, and oxygen, of course, 0 again, okay? So you do your maths, this answer, right, which is, of course, 8. This is an objective question. So it's, you do this in your paper 2, you get 4 marks. Do here, you get 1 mark only. Okay, now here is a bit different because this is an ionic compound. Never mind. As long as you see the heat of formation is here, formation here, formation, you can apply the formula again. Quite simple, say. So, and heating this one, of course, this, of course, is a form 4 reaction called heat thermal decomposition of nitrates. Okay, here oxides, and O2 plus oxygen, but here there's no oxygen unless you heat very strongly for MnO2. Don't care. As long as you give the equation, then you do it. Right? Same thing here. Right? The equation here, heat of reaction equals to, again, this is your products. So MnO2 is -520, same thing, right? So very simple answer is on here. Okay. So these are ionic compounds, and of course now we go to the next one here. Very simple. Okay. So now this is of course the combustion of ethanol. All right. We give again formation. See, very simple here. So as long as you see the heat formation is given, you can apply a formula. You have to go by the circle method. Is pretty. The one is pretty well tedious in a way lah. Okay. So make sure here you expect to know how to write the equation here. Right, 1 mole of the compound fully combusted. So two carbon here. Of course, here is H2. Somehow I rub it off. Okay, so 6 hydrogen here, so 3 here. Right. So here's 4 oxygen. Here's 3, 7. So it's 1 here, 3 here, 7. Okay. So again, this 2 times carbon dioxide is what? Is 286. So it's 286 here. Sorry. They're correct. 3 of water. Did I make a mistake? Oh, I made a mistake. Sorry. 3 water. Oh yeah, correct. Yeah. Okay. So see, I also can make mistake. Right? 2 times carbon monoxide. Carbon dioxide is not here. Correct. My eyes are blind. Okay, correct. 3 times water is 2861. Okay. Minus here, and this of your ethanol minus 277, and of course it's 3 times 0. Why oxygen is 0 element? Okay. So you get the answer here, which is part B. Okay, so quite simple. Now here is another one. Again, right? They give you everything here, and of course they say it's formation again. Iron sulfide is a fat gas. Okay, next to oxygen to give you sulfur dioxide, and inside is an acidic gas. See here, formation. Yeah. So this is all formation. They didn't tell you, right? But they put the F here, so you have to notice that it's all formation. Otherwise, you trap. Okay, same thing applies. Okay, 2 times water. Here you are. 2 times SO2. Here you are. The reagents, iron sulfide. Here 2 times CCN. Here you are. Oxygen is 0. Again, you make sure the minus sign is dealt with. But the answer is this one here, which is of course B. Simple, isn't it? So remember, this is very simple finish. Okay. So remember how to use the formula for the summation of heat of formation of products minus summation of heat of formation for reagents for any reaction will do. Okay. Now next one is a bit more tricky. Now normally this one comes together. Your bond energy and heat of atomization for elements come together. Okay. They are a way related. Okay. Now let me show you the difference. Okay. Now bond energy is for covalent bonds. Okay. For example, chlorine, okay, Cl2 is Cl-Cl. So that this is called 1 mole. 1 mole of covalent bond. Covalent bond of chlorine. Okay, Cl2 is 1 mole, okay? Right? 1 mole. It's called 1 mole, say 1 mole of bonds. Okay? So, and it's always to break. To break means that you require energy, it's always endothermic, always positive, right? Because you can see here, the syllabus require you to say that. Okay, it's very important. See, now bond energy. Look at here. Bond energy delta H is positive because whenever say bond energy, it always means the breaking of bonds. Of course, forming the bonds is called bond energy, but it's negative, isn't it? But they say the syllabus say whenever they talk about bond energy, it's always positive. That's why if we refer to all your data in here, I think I told you this before, but I'm going to go tell it again, okay? So all the data here, see now, bond energy, right? Here, let me just put the color, see bond energy. See, all is positive here, positive. So bond energy in the syllabus, it refers to the breaking of bonds, breaking of 1 mole of covalent bonds. Can be single bonds, can be triple bonds, can be double bonds, single bonds. Okay, whatever is it between the 2 of them, the diatomic fellows here, the bond broken is called the bond energy. Okay, so that must be clear, right? Now here, how about the standard enthalpy change for atomization? It's different. It's the enthalpy change when 1 mole of the gaseous atoms. Now this one here, gaseous atoms, is produced. That means this is about the product. See here, when you break 1 mole, you get 2 moles of Cl gas. See, here's 2 moles of Cl gas. No, this is 2 moles of Cl atoms, and it's gaseous. 2, the delta H, the bond energy is equal to what? Positive 242. Okay, sometimes it's 244. Don't care lah. As long as you take your thing here, right? It's 24. Here is 242. I think. Right? Sometimes they say 24. See here 242. Sometimes they give you 244. Just follow what they give you. Okay, but normally data bullet is 242. Okay, right? So here that means here to break 1 mole of your covalent bonds, you require 242, and it forms 2 moles. 2 moles of the product. Okay. Now, but if you talk about the heat of atomization is a heat change when 1 mole of gaseous atoms are produced, which means we talk about chlorine, okay? Cl2 here, or Cl2 here, right? I must form 1 mole. Here's 1 mole. 1 mole of gaseous atoms, 1 mole only. Okay, it's produced from its element. In standard conditions, means that this one must follow here. That means chlorine is what? Chlorine is gas here. Because if it's iodine, okay. It means here, standard condition. So there are 3 marks in 1, 2, 3. So to form 1 mole here, I must put half here. That's why the heat of atomization is what? Is half of this value here is plus 121 kilojoules per mole. Because it's here we are interested in the products. Here we're interested in the reagents, not the 1 mole of covalent bonds of reagents. Right? That's why there's a question that actually asks you the reason. Okay. So remember, here is to break 1 mole of covalent bonds. Here's to form 1 mole of the gaseous atoms from its elements in the standard state. That means that elements here means Cl2. Standard state means what? Gas. Because if it's iodine, right, as you see later, like here, right, which equation represents the standard enthalpy change for atomization, okay, of bromine? So remember now here, this is for bromine. If it's a Boyle energy, it must be 1 mole of covalent bonds broken in the what? In the gaseous state here. See, in the gaseous phase, 1 mole of in the gaseous phase. That means the bromine, chlorine, all must be in the gaseous phase. That means that here. That means this is a bond energy in 1 mole of covalent bonds broken in the gaseous phase. Br, to give 2 moles of, so it's bond, this is a bond energy. But here atomization, it means what? 1 mole of the gaseous atoms found from its elements at standard state. At standard conditions, that means at the standard conditions, which is temperature equals to 20 standard conditions, okay? Again, it's playing me up all the time. Okay. Standard conditions is what? As standard conditions. Means temperature is 25. Right? Pressure equals to atmosphere. That means this one here is liquid, no, bromine. No. So this here to here is called atomization. Right now, bromine, if you look at carefully here, they ask you this question afterwards, I'm sure you are. Okay, here we are. Bromine, Br2, is 193. Now this is the bond energy 193, 193. This is 193. 193. Now there's a question that here goes here. Must show you, okay? Now bromine, 193. Bond energy is 193. Now chlorine is 242. Atomization is 121. Half is correct, isn't it? This produce a Cl gas. This produce 2 moles of Cl gas, okay? Right. But here it's not half, it's not half. This is half, yeah, because this produce 2F gas, this produce F gas, 1 mole, okay? So why is it not half? Why is bigger than this one? Because we start at different points. Now see now, here, I put down here. See, bromine, if atomization, it must say the element, which is here, Br2, it has what? Standard state liquid at standard conditions, which is 25 degrees centigrade and 1 atmosphere. That means that for me to here, it takes on another route first. It must become gas first, right? To do the bond energy. That means that now this is a change of state, right? Same temperature, same state. It's got a latent heat of evaporation. That means it will absorb heat here. See now? So there's a heat absorb here, and there's also a heat absorb here. Of course, now this is of course a bond energy, okay, right? Okay, half of bond energy. Why half bond energy? Because I want to make half one only one. Because if the full thing will be two BRs, yeah, be 2 BR here. I don't want 2 BR here. So that's why, because I started with Br2 liquid. Iodine same. Like here, see the question here, right? For which equation does the enthalpy change correspond to the enthalpy change of atomization? Which means I want to make this one here, this is called heat of atomization of iodine. 1 mole of gaseous atoms from its element at standard state, okay? At standard condition, this is solid here. So for it to go here, right, I must go to I do half of it. Why half? Because I want to make 1 mole to gaseous state. Now this is called what? Your latent heat of what? What? Sublimation. Okay, you learn in form 5 now. Now from here, yes, this will be half of 1 energy. That's why it's not. This one is not. This one here is not half of your 1 energy because it takes another route. You need to plus energy here. So of course the answer is what? Okay. Remember, if atomization, it must be from its elements at standard states, which is here. Elements standard state, and must be 1 mole. Answer is B. Here same. Standard state element at the standard conditions, right? And 1 mole. C answer. Okay? So you can see here they ask you the question like this, right? So heat of atomization and 1 energy, similar in the sense that they both will produce the gaseous atoms. But 1 energy will produce 2 moles of gaseous atom. Heat of atomization only 1 mole. And also depends on the standard states, right? At STP. Also, or rather temperature and pressure. Okay? So now this way they ask you. For fluorine and chlorine, the enthalpy change of atomization are half the value of the 1 energy. It's true, isn't it? Right? Because you, for this case here, what you want is only 1 mole of gaseous atoms. This one here, 1 energy, to break 1 mole of the covalent bond, they will always produce 2 moles of your gaseous atom. For bromine and iodine, the enthalpy change of atomization are much more than this. Why? All they want is, they say here, okay, show you the answer, okay? All they want is fluorine and chlorine are gases, all right? See, don't explain all this latent heat, okay? Gases, whereas bromine is liquid and iodine is solid. This 1 mark already. Either one is 1 mark, okay? So, of course, iodine change of state, these 2 change of state. If we are explaining latent heat, also they give you correct. Okay, so it's very simple. They don't ask you for detailed explanation. Okay, so now this is the one here. Of course, not this question here. So how do we tackle? When do we use 1 energy to tackle the question now? The question is very simple. It's almost same like the first one there. Okay, I'll show you how to do it so that it's very simple for you. Right now, they give you the standard pitch formation of iodine monochloride is this one here. Now they didn't tell you here. Remember not? Because they didn't tell you the states of this now. Actually, it's liquid, but they didn't tell you. So it's okay. Okay, don't worry, they will lead you on in the question. Okay, iodine monochloride. Okay, now this is called interhalogenic compounds. It means both belong to the same same group. Actually, it's I. You want to know? Okay, it's I. The cross dot and cross here, isn't it? Because they are both group 7. Okay, so it's like this, right? So the formation, which means this is the one. I want to put red color so that you will see the difference. I done it earlier so that I can go faster. You see, right? So remember this heat of formation. Formation means 1 mole of the compound formed from its elements. Right? Now they didn't say they say standard here, but you know, is of course standard here should be solid, is it? But no, they lead you on. As I said, this formation they didn't tell you even this is this liquid. They didn't tell you, so they want all. They want all in 1 energies, so they will lead you. Okay, they make it simpler for you. Use the information and this information means one and the 1 energies. They don't ask you for the latent heat or this stuff. Don't care. Follow the question. Read the question carefully. Okay, 1 energies of iodine and so forth here. So 1 energy, that means right, means here. That means of course you want to draw here. You go to I gas. Okay, this go to Cl gas. Okay, half means here plus here. You want to do the whole thing, but simpler one, of course, if it's all gas here, like a form 5, like all gas here, all you do is to bonds broken, bonds from the easiest way, okay. So here, of course, here to here is bond broken, okay. So right, half bond broken means this is a bond energy. Half plus means you bond break is endothermic. Cl2, of course, half means half plus 2 for 2. Okay, so total amount of is here. So it's plus, you plus everything up, plus 196.5. So on this side here, also gas. So it's bonds formed, isn't it? So bonds formed. So 1 bonds broken, 2 bonds formed. This is the simplest you can do. You can do other ways, so up to you, but I will tell you the simplest way. This is how the marking scheme will be. Okay. So bond sum is ICl. Okay, there's X here. Now, remember, now there are two ways to do it. I like to put, well, bond sum is isotonic minus X. But X is actually positive now because as I told you, bond energy is always positive. Yeah. So the bond sum is minus X. So remember, so you got here. So basically, this is this one, right? This reaction here, the whole reaction is this one, the energy here, right, plus this energy here. Easy. Okay, the total here plus this total here. Or if you use here as positive, it will be total here minus this total here. It means you change this to minus because heat is given out. Okay, so up to you. So I like to use this whole thing. It means this whole reaction here, right? Minus 24.0 is equals to this total here, right? 9 plus here I put a minus sign because it's heat given out. But if you use here positive, then it must be a minus here. Then here is positive. Then the answer will be as it is. Okay, you think about it, it's quite simple. It's just maths. Okay, this is the answer here. All right. So bond energy, you just put bonds broken, bonds formed, easier for you. Now another one. Okay. Now here, the important thing is you must know how to draw the diagram for the bonds. Right. The equation for complete combustion of ethyne means what? Triple bond. Okay, it's your acetylate in your form 5. You have to know this. Okay, now, right? Use appropriate bond data for data booklet to calculate the value. Okay, now, it means you ask a bond energy now. Excuse me. Okay, so draw it out. Oxygen double bond, carbon dioxide double bond here. Okay, form 5 is what you do now. So bonds broken. These are all bonds broken here. To break 1 triple bond. To break 2 carbon hydrogen bond. 1, 2 here. So 2. Okay, times this one here. 502 oxygen bond. Okay, now all this can be gotten from your data booklet. Okay, have a look at carbon double bond carbon. Okay. Okay. Carbon triple bond. I think it's over this side here. See here. Okay. Right. Triple bond. 840. All right. So here is 840. Positive. Okay. That means I'm breaking the bond. CH bonds. Okay, 2 of them. Why? Here's 1, here's 1. Okay, oxygen 502 moles. So total is on here. Okay, and here is this one here. Bonds formed. 4 carbon dioxide for 1 molecule is 2 of them. So it's 2 moles here is times 2. So 4 of them. Okay. Minus. I put minus here. You can put plus here. You want to plus 740. That means here must be minus here. Okay, right? When you add them up, just put a minus sign here. It's up to you, because I think bonds form is negative. Okay, so here's this plus this then. Okay, same thing here. You get the answer here. 3 marks. Easy, isn't it? All right. So bonds formed, bonds broken for covalent bonds. Use the bond energy. Get the whole thing here. Now here, same thing again. Right? Fluorine, of course, is FF. Chlorine is Cl. So 3 moles broken. So 3 times 158. You can see here is 158. Fluorine. Fluorine. Where's fluorine? Oh, here. Homolytic. Homonuclear. Fluorine. Okay. 158. Okay. You can check all the answers here if you want to. Right. Chlorine is 242. And of course, you add them up. So this is the total bonds broken. Bonds formed. Remember C. So you have 3 bonds here. F. You have to draw it out to convert yourself. So there's 1 mole got 3. So 2 moles got 6. Right? I put 6x up and put 6 up to you. Okay. So heat of reaction is on here. It's equal to this plus this. Okay. Right? You just plus it out. The x here will be negative 1. Okay. But bond energy is always positive, so you change it. If you want to put positive here, you can just put minus here, and here become negative. It's positive. So. Okay, now up to you one. Okay, this is variable. I like to use here is negative right now. Okay, all right. So here 6x, right? So here remember you bring over here is negative. That means here is negative, but bond energy is always positive. Okay, right? Now all these are same. Of course, now this case here is a bit tricky in the sense that chlorine dioxide. Okay, this is used in your cube bacteria in your swimming pool. Okay, from this one here. So this is the thing here. You don't have to draw the cross and don't care because they tell you that it is true like that. Okay, now see the chlorine atom is in the middle of the C7 bond. So it's in the middle. That means 2 must be here. Okay, so chlorine oxygen bond is 278, so forth. Okay, and so other things is a data booklet, which means bond energy as well. Why? Because all of them are covalent now. To use covalent bond, you must be gaseous. All must be gas. Okay, it's the first thing about. Okay, to use bond energy, all must be gas. Remember not gaseous state, okay? Not at the standard room temperature pressure. Cannot. That one is for heat of atomization. Okay, so bonds broken. Right here, 4 of them. 1 mole is 2 ClO. 2 moles is 4 of them. Right. So it's like here. Bonds formed. Cl oxygen will be 2 times. Okay, 2. Not 0. Okay, 0 is for enthalpy change. So 2 times. Okay, minus 496. I put minus. I said why? Because heat is given up. That's why I just plus here. Okay, so the answer is this one here. Okay, so you can do by yourself. It's quite simple, right? Here's another simple one. All right, you can do by yourself. Now here is a bit different. I brought up some different things as well. Now this is called cyclopropane, and this is called skeletal diagram, which I have not done before with organic chemistry. Never mind. So it reduces the whole thing. They don't draw carbon and hydrogen there. So this is actually this one here. Okay, so it's a triangle thing, carbon, carbon, carbon. Okay, so in fact there are in one molecule there are 3 carbon bonds. Okay, all covalent. There are 6 carbon hydrogen bonds. Okay, 6 carbon hydrogen bonds. That's all you need to know. Okay, then temperature change of formation, of course, for cyclopropane is on formation means what? 1 mole here. I use blue so they can see easier. Okay, see 1 mole. Here's 1 mole. 1 mole. 1 mole is formed from its elements. Elements. As standard state, it means a solid here, graphite, gas here. Okay, so it's the thing from here. Don't care what is this. Okay, actually it's gas. Okay, right. So it's gas. Right. So here, what they give one energy, you can get from the data booklet. It's also from data booklet, but they didn't say use data booklet, so which means they give it to you. Okay, if they use the data booklet, that means you better use data booklet. What value of the average bond energy? You can read up yourself why average, because different atoms may join to carbon or here, so they will cause difference in polarity. That's why not all CH bonds are the same. So take average, okay? Because the carbon here can be joined to oxygen, fluorine here, so there's a difference in electronegativity. So the CH bond is not always the same. It's just a bit different. That's why it's average, okay? You can read up yourself the one I don't want to talk about, okay? So here, right? Remember, they say atomization of graphite, okay, from here to here. 1 mole form is plus 717, okay? So 3 moles form 3 times, okay? Yeah, and the enthalpy bond energy for HH to here, I'm breaking 3 bonds to form 6, so 3 times 4, 3, 6, yeah. So now from your cyclopropane, now I can go this way or this way, it's okay, up to me, man. So if I go this way, right, that means I'm forming bonds here, right? Also, I'm breaking bonds here, I'm breaking the CC bond. That means the answer will ultimately give me a positive sign. Because why? Because I'm forming now, okay? Right? So I'm breaking the bonds, okay? So it's not here, right? So it's 3. I'm breaking the bond. So the X will give me the actual value there, right? So remember, bond energy is breaking. So I'm breaking 3, 1, 2, 3 carbon bond and 6 of CH bond. Okay. So I put this as X. Here is 6 times this one here, right? So the first root here to here and here to here. Okay. So 553.3 plus 3x plus 6 times positive 410. Why positive? Because I'm breaking the bonds. Okay, so work it out. I'll get this answer. 946 positive. See, ultimately come up as positive. So of course it's D. Okay. Now last one before I go into the last bit. So I am finishing on time, which is very good. Okay. Now here, of course, this answer because I go in space, so I do it up here. Okay. So sulfur consists of molecules up to 8 atoms covalent bond together. Now this is Form 5 you learned before, okay? Sulfur is like a crown, you know. It's all these bonds are covalent bonds, strong bonds, okay? So it's like a crown. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's S8. So to break all these bonds is a sulfur bonds, okay? Right? Okay, so sulfur dioxide, they give you this one here. They're very kind, give you the formula and the one here. Enthalpy combustion of 1 mole. Remember what is 1 mole, right? Is minus 2376. That's why sulfur burns with blue flame. Like in hell, it says blue color. It's very hot. It's a lot of sulfur, a lot of heat given out. So now to represent this here of combustion, right? It's here, right? I put here. It means 1 mole. That means S8. Okay, plus oxygen, right? SO2. That means 16 here must be 8 here. Okay, so right now, so how do you do it? You can see here they give you, all right? And you're required to break 1 mole into its gaseous atoms. That means S8 goes to 8 of S is solid here, right? Gaseous now. Okay, from its elements at standard state, okay, standard conditions. Okay, so here to here, so here atomization, positive now, it's positive. Okay, so also give 1 enthalpy of 1 energy is 496. So here, right? So here is your the breakout heat of atomization. Here's your boil energy, okay, right? 16 O, right? This is 8 times the same. So from plus here, of course, you get how many of these bonds from? 8 of these molecules. So 8 times 2, because every molecule here got only one, right? Here's 2 times 8. So times 8 is 16. Okay, so quite simple. Hess law, right? Now this bond form, right? You put reverse. I put red color. If reverse, I see. Where's the red color? Ayo, sorry. Okay, if you put reverse. Okay, you put reverse. Right? That means it will be what? It will be here to here. It will be positive now, right? Here to here, this will be negative now. Okay, right now because it's bond form. Right. So up to you. Right? You put this now. What I'm doing, I do this way. Here to here, here to here, and here to here. So this one here. Sorry, this one here. Okay, the first row minus, okay, equals to this one here plus this one here, okay, plus this one here, right? Okay, right. You put from this way here, that means this one will be all this side lah, right? Doesn't matter, it's the same thing, okay? But you must understand bond energy is always positive one. So you solve the maths, you get this answer. Here, of course, the key thing is S8 lah, okay? Okay, now I think I finished most of the thing here, all right? You can do it by yourself. This is also very bond energy. Okay, very simple lah. Okay, also this bond energy. Okay, all this. Of course, in this case, you have to know the formula. Like here, carbon. Okay, this you learn Form 5, not okay, right? 1 chlorine here is all hydrogen here. Okay, so for 1 mole here, there's bonds form is 1 C, right? There are 5 again. It playing me out. Again, I tell you, this is crazy. I didn't download the thing, that's why. Sorry, okay, I'll do it again. Okay, as long as it works, okay? So 5 of your C is CC bond, 5 of the CH bond, okay, and 1 of your CCl bond. So this is the bonds form, okay? So here is, of course, this is 6 CH bonds, okay? So you need to do all these things to get your answer, okay? Very simple. This is vapor pressure, you can look it up, your answer yourself. Now this is like a trick question, here. It's all gas here, gas here, gas here. Oh, you think you will use bond energy? No, formation, So, sometimes you have to read the question carefully, okay? Formation here, so you use the formula easier. Okay, all right? Okay, now this one here. This one is AS method. Heat of solution, you can see here the heat change for substance. Heat change when 1 mole of the substance is dissolved, okay, to what from infinite dilution, which means, let's say, for example, which I'm going to give you afterwards there, let's say for now magnesium sulfate. Okay, it exists in two forms. One is, of course, anhydrous. This is called anhydrous. I explain first, okay? Anhydrous means no water or crystallization. Okay, plus AQ, that means a lot of water. And you add water until no more heat change, you get Mg. That means it dissolves completely to form quite infinite dilution. It means you add water, the heat will keep giving up until the point where no more heat change here. No further heat change here. More water is added. Okay, equals here plus SO4 2 minus equals now. This is called your heat of solution. Solution of anhydrous. You must put anhydrous. Okay. Now there's another one, of course, when you start with magnesium sulfate hydrated, 7 water of crystallization. This is the common one you use to heat your crystals to find how many moles of water here. Now, this is a solid. Both are solid. Plus equals. Also give you the same thing here. We go to here. Okay. Now this also called the heat of solution, but for hydrated. Okay. Right. Now from here to here, you just add water enough just to, it's still very solid. No, now this is called the heat of hydration. This is for AS. For A2 is a bit different already. A2 you talk about less energy and so forth. So now this is the definition, right, for A2. Okay, heat of hydration when 1 mole of the ions, okay, means here's not ions, here's the whole thing about, here's the solid. Ions or gaseous ions dissolved in water form. Okay, that means this is the correct one for A2. But AS, this is the one. The hydration of an anhydrous salt, very important. Okay, you do this in your A2. A2. This is your AS. Okay, I'll show you the question. When 1 mole of the anhydrous, okay, this is obviously a solid. Okay, completely hydrated to form 1 mole of the hydrated solid. Both are solids here. Solid. Okay, right. The heat of solution. Again, I repeat here. Right. This is from past year question. This is your marking scheme. 1 mole of the substance dissolved in the solution to form infinite dilution. Here same. When 1 mole of the compound dissolved completely to form infinite dilution. Okay, external conditions. Okay, I'm going to show you the question here. I did already. Now this is from a book. See, anhydrous salt. Now this is solid here. It's a hydration to hydrogen salt. This is a solid, which means to say if I got magnesium sulfate here, solid, goes to magnesium sulfate, 7H2O, also solid. This is called the hydration. When 1 mole of the anhydrous salt is hydrated to form 1 mole of your hydrated solid salt. But here to here is called your heat of what? Heat of solution. Of what? Of your anhydrous salt. Here is called your heat of solution also. Of what? Of your hydrated salt. So both ways I can hear. Okay, dilute solution. That means it's your infinite dilution. Okay, right? Okay, now I can see this. That means I can calculate this one. Okay, right? This plus this equals to this. Okay, this is what they did. Okay, right here. Right now, this is the question that came out. I just want to do it for you, right? Together, I did already, so I just explained to you. Okay, easier for me to do the whole thing again. Save time. Okay, you can go back and slowly read over again, and then see the video again, whatever. Enthalpy change of hydrations now. See now, of anhydrous, magnesium sulfate. Okay, say hydration here, which means to say that, well, I'm going to MgSO4 solid. I'm going to plus here some water. Actually, it's 7 water. Okay, right? Can be calculated. Okay, 7 water. Okay. Okay, liquid here to form your MgSO4 dot 7H2O. Now this solid, no. This is called your heat of what? Going to here. I don't know why. It's something when I do there, it just won't work anymore. Do again. Right, I touch here cannot really. This is called heat of what? Heat of what? Hydration, right? Of anhydrous, right? Okay, can be carried out 2 separate experiments. Okay, the first one. The first experiment, 45.00 grams of water. Here, see, draw diagram, right? 45.00 grams of water was weighed in a polyethylene cup, and 3.01 grams of MgSO4. It means no water. This is anhydrous. Okay, we have and put inside and stirred until completely dissolved. That means from an aqueous solution. Temperature rose from, that means it's exothermic. Right? Calculate the heat change, transfer, and so forth. Of course, you use delta H MC theta. Now remember, you don't, the M here is the mass, you don't put, the solid don't count one, only the water will count. Okay. So 45 grams, these grams, and 4.1 heat capacity, then change of, you don't have to convert to Kelvin because they minus off anyway. You convert the minus off the 273, doesn't matter. So that's in joules, no? Because it's in grams. Okay, it's in joules. So this value here is negative. Why? Because heat temperature increase. Okay, so this is the first part here. So they ask you to find out the number of moles is over the MR 120. So this number of moles, because why? For the hydration is 1 mole. See, 1 mole. The definition is here, right? When 1 mole of the anhydrous salt. Okay, so here is 0. How much? Here is 0.025 moles of anhydrous and magnesium sulfate. Okay, right? To give out how much? Minus 2125.53 joules. So can change it to kilojoules. Means 2.12553 kilojoules. Okay. Okay. So easier. That's why it's always kilo. So 1 mole equals how much? So that's what I did here. Okay. Right. Right. So 1 mole is 300,123. So it's 85. Remember? Right. Okay, so from here to here, this is the heat of solution, is minus. Why? Temperature is going up. Yep. Okay, so this is the from here to here. Now this is the equation. Remember, this is heat of solution now. Why? Because they form the infinite dilution one. Okay. Okay. Now next one here. They say, well, the second experiment, enthalpy change for solution for hydrated salt. Yeah. Okay. That means this one here. MgSO4.7, they give you here already. Now this is hydrogen salt, 7H2O, solid plus aqueous. Okay, to find what? Mg2 plus aqueous plus what? SO42 minus aqueous. Now this one is given as this one here. That means from here, like here, from here to here. Now here, this part is your heat of hydration. Okay, this is anhydrous. This is your hydrated. This is a heat of hydration. See now, okay? So this is the first one you did the experiment, right? It's minus 85. Here they give you here, okay? 9.6 here. This is positive. This is negative. This is 0.0, okay? So by Hett's law, this plus this equals to this. Very simple. Then you can find your heat of hydration of anhydrous magnesium sulfate. This one here. Remember, the sign is very important, right? You get everything is negative one. So you put the arrow correctly, you get negative value here. Okay, right? Simple, isn't it? All right. Now here is one question. Here is a bit off the key, but you can see how they being asked here. Okay. This data bullet is relevant to the question. Enthalpy change of formation of hydrated calcium ions is the enthalpy change of the. Okay, let me. This one is called the heat of formation of hydrated. All these terms are very specific. Hydrated calcium ion. Okay, that means this one here. Okay, to form 1 mole, right, from its elements, and must be ions here. So the following enthalpy changes are not quoted, and so forth. So how does this change occur? Now I repeat this one here. Okay, calcium solid plus equals minus. Actually, better to put minus. Should put plus here. Normally put plus 2 electrons here. Okay. So to form this one here, what must happen first? it first must be atomized now. Okay, this is our heat of atomization, which is where? Which is here. Okay, atomization. Okay, go to calcium gas or heat of 1 mole of the gaseous atom formed from its elements at standard states. Calcium is solid one. Okay, at 25 is segregate, so it's positive here. Now, second, of course, it must undergo 2 first and second IE not. Okay, IE which is done with the teacher. Okay, so now this is the first and second ion. Okay, right? Plus 2 electrons here, and of course this now undergoes what? Hydration. Okay, this is for hydration. This is the actually the A2 one. When 1 mole of the ions are completely hydrated, this is where it came out. That means they also use it here. Okay, now here is given as this. 1 mole is hydrated. Yeah. Okay. So what is this heat change? Remember, Hess law here to here is equal to here plus here now. Okay. So here plus here plus here is equal to here. Okay, Hess law. Again, you solve is plus 352. And do it yourself again. Okay. So great. We are finishing now. The fourth type of calculation is very simple, which is in form 4, form 5. It's called the heat of neutralization. Now, this is very important definition here. Okay, the heat of neutralization is the heat of when 1 mole of water is formed. When when 1 mole of water is formed. So heat evolved when 1 mole of water is formed. When 1 mole of H plus or 1 mole of OH minus, understand condition, okay? It's always minus 57.3. For strong acids and strong base, because why? They completely ionize. Right? They don't have to absorb heat to break the bond energy. But lower for weak acid, weak base, okay? It's absorbed to completely dissociate, right? Okay. So now, so this is called your heat of neutralization, delta H, neutralization. Okay. Right, it's always minus 57.3 kilojoules per mole. Okay, so now here, because there's 2 moles of water here, because this one here is 2 moles of water here, so it's times 2. So it's 57.2 from 3 times 2. It's about 114. Right here. So using this form information is the most likely value for enthalpy change for result. So as long as 2 moles here, you don't care, it'll be same as here. Because it's like strong acid and strong base. Okay? Strong acid, strong base. Okay? It cannot be more than this. Ridiculous, isn't it? Now here's another one which they ask like that. Remember this pathway, it means this is always what? Delta is always what? It's always exothermic. Atomization is always endothermic. It's not. Right? Because why? You always need energy to break, right? To break bonds, Okay, it's always positive atomization. Because solid or liquid or gas, to form gaseous atom, you must break bonds. So it's always positive. Combustion is always negative. Formation can be positive or negative. Neutralization is always negative. No. This one here comes up. Okay, so obviously, which cannot apply this one. Okay, our next one here is a very simple one. The table shows the enthalpy change for the neutralization. Okay, per mole water here. Of course, strong acid, strong base, 57. No 3, never mind. Less than that, it means this must be a weak acid. It must be a weak base. Same as a strong base. So simple. Weak acid, this one, these 2 here, right? Q, weak base, this one here always stay this strong. So answer is A. Okay. So guys, we are done. Okay, so we have finished this stop it. Okay, so we have finished your thermochemistry already. So the next one we go, of course, is your, I think, is electrolysis. Okay, so I'll see you next time. Bye bye.